Hello students, last class we solved some numerical problems based on zero order reaction and first order reaction. Now let us study or discuss the another portion of this chapter, that is collision theory. What is this collision theory or collision theory? Generally, this theory is forwarded by Max Strong and William Lewis, and this theory is generally based on kinetic theory of gases. So according to kinetic theory of gases, all gases are consist of very small minute particles, that is called molecules. In this way, same thing. The reactants are made up of molecules, and the molecules are always in a state of random motion. Okay, so first point is that collision theory, all the reactants are consist of molecules. So in notes you have provided what are the postulates of this collision theory. So all the reactants are consist of molecules, and the molecules are always in a state of random motion. The molecules are always in a state of random motion, and when they move, at that time the molecules collide with each other. So molecules are always in a state of random motion and hence go on colliding with each other. So the random motion, due to which they collide with each other. Okay, they collide with each other. So the number of collisions that takes place in unit volume per unit time. So the number of collision that takes place per second per unit volume is known as collision frequency. That is known as your collision frequency. Okay, so the number of molecules that collide in unit time or unit second in unit volume is known as collision frequency. Okay, next, a chemical reaction takes place due to the collision of molecules. So chemical reaction takes place due to this collision of molecules, but all the collisions, so when the molecules move randomly and they collide with each other, at that time that is called collision takes place, and due to this collision only the reaction takes place. So but remember, all the collisions do not bring about a chemical reaction. All the collisions do not bring about a chemical reaction. So this collision of molecules, generally chemical reaction takes place, but all the collisions do not bring about the chemical reaction. Only effective collisions. Effective collisions bring about. Only effective collision bring about the chemical reaction. The chemical reaction. Okay, so what is then? All common collisions do not bring about the reaction. Only the effective collisions bring about the reaction. So what is the condition for this effective collision? To bring about the effective collision, to get the effective collision, the molecules have to cross two barriers. The molecules have to cross two barriers. Molecules have to cross two barriers. One is energy barrier, also called potential barrier. Energy or potential barrier, and another orientation barrier. Okay, so there are two barriers. One is energy barrier, or also called energy or potential barrier. Another is orientation barrier. So what is this energy barrier? Energy barrier means all the molecules should possess a certain minimum energy where the reaction starts, and that energy is called threshold energy. That energy is called threshold energy. So all the molecules which bring these effective collisions, all the molecules which brings this effective collision, they should have greater than or equal to the threshold energy. They should have energy greater than or equal to the threshold energy. So for the only effective collisions bring about the chemical reaction. So to bring about the effective collision, the molecules have to cross two barriers, energy barrier and orientation barrier. So energy barrier means all the molecule which get effective collision, they should have energy greater than or equal to threshold energy. Greater than or equal to threshold energy. And another, the molecule should properly oriented. The molecule should properly oriented. For example, if this is given, one example, look here, this is the NO2 gas is given, and another way, another molecule of suppose NO2 is given. In this case, suppose two molecules are there, but no product will be formed. Although they get the effective collision threshold energy. So this plus this, these two, when these molecules approach each other, when they collide with each other, the nitrogen collide with oxygen. In this way, they do not bring about any chemical, any product. But if properly oriented, that is ONO is like this, and another way is like this, then these two molecules, nitrogen, if this orientation is properly, if this alignment is properly, then they give rise to this product, that is N2O4. So for the formation of N2O4, this molecule of NO2, they should properly oriented. So in this way, this is known as your collision frequency. That is, gases are or reactants are consist of molecules, and the molecules are always in a random motion. They collide with each other, and due to this collision of molecules, chemical reaction takes place. But all the collisions do not bring about the chemical reaction. Only the effective collisions bring about the chemical reaction. And to get this effective collision, the molecule should have to cross two barriers. One is energy barrier, that means they should have greater than or equal to threshold energy, and another barrier is orientation barrier, that means the molecule should properly oriented. So this is some idea about collision theory. But here we find another term, that is there is a term that is known as threshold energy. So what is this threshold energy? So this is the limiting value of reaction. Next come to threshold energy. Okay, so what is this threshold energy? You know, hydrogen and oxygen reacts to form water. In atmosphere, there are so much amount of hydrogen and so much amount of oxygen, but they do not combine to form water. Okay, so in this way, there are, carbon is there in atmosphere, in our surrounding, so many carbon particles are there, and oxygen are there, and this carbon oxygen do not combine automatically to form this carbon dioxide gas. So what happens? Why this happens? Because the molecules or the reactants do not achieve a certain minimum energy where the reaction starts. So to start a reaction, all the molecules or the reactant species that should have to reach at a minimum amount of energy. They should have to reach at a minimum amount of energy, and that energy is called threshold energy, where the reaction just starts. Okay, where the reaction starts, that is known as threshold energy. So generally all the reactant species, that may be our terms molecules, they have less energy than that of all the reactants, they possesses less energy than that of threshold energy. So what is threshold energy? The minimum amount of energy where a reaction starts, the certain minimum amount of energy that should possessed by the reactant molecules to start a reaction. The minimum amount of energy that should be possessed by the reactant molecules, the minimum amount of energy that should be possessed by the reactant molecules to bring about a chemical reaction, to start a chemical reaction, is known as threshold energy and is represented by ETH. That is threshold energy. Next, so generally all the reactant molecules have less energy than that of this threshold energy. And how these reactant molecules reach at the threshold energy? In this way, we have to supply some amount of energy to the reactant molecules so that this will achieve the threshold energy. This will reach at the threshold energy. So the extra minimum amount of energy, the extra amount of energy supplied to the reactant molecules, the extra amount of energy supplied to the reactant molecules to achieve the threshold energy is known as activation energy, represented as EA. Okay, activation energy represented as EA, threshold energy ETH. So all the reactant molecules, they have less amount of energy and when we supply some extra energy so that the reactant molecules achieve this threshold energy where the reaction starts. So the minimum amount of energy where the reaction starts is known as threshold energy, and the amount of energy supplied to the reactant molecules to reach at the threshold energy is known as activation energy. Okay, so this can be better understood if we draw a energy profile diagram. Okay, so this is the reaction progress, how a reaction progress, and this is energy. Suppose this is the energy of reactants, okay, and this when the time progress, then the reaction starts like this. So we supply some amount of energy, then it reaches at a maximum, then it comes back and like this. Okay, so this energy is here, suppose product, here energy reactant. So up to this is known as your energy of reactant, and this much is known as energy of product. This is energy of product. And what is the difference between energy of reactant and energy of product? Del E. This is known as your energy of reaction, okay, or enthalpy of reaction. This is known as your enthalpy of reaction, or we can write del H, enthalpy of reaction. And this energy, whether just all the reactant molecules get excited and they get some energy, and where the reaction starts, and this energy is known as your threshold energy. And what energy is supplied here? What energy we have supplied here from this to this is known as your activation energy. So this is known as your activation energy. Okay, so here EA equal to ETH minus ER. So energy of activation equal to threshold energy minus energy of the reactants. Okay, so this is known as your activation energy. Okay, another way, if we consider a reversible reaction, then the reactant molecules possesses threshold energy, then reaction starts, and then it will form the product. Okay, so this difference is known as this is your energy of product. Okay, again when this product gets some energy, then this will go to this threshold energy, then the reactant will be formed. So look here we have considered energy of reactant and energy of product. For a reversible reaction, if we consider a reversible, reaction, look here the energy profile diagram. Here ER and EP, energy of reactant is more and energy of product, and this is the energy of activation in reactant side, and this is the energy of product in energy of activation in product side. So for a reversible reaction, if ER is greater than EP, energy of reactant is greater than energy of product, then activation energy of reactant is less than activation energy of product. From this diagram you can find out. Okay. Similarly, to find out the enthalpy of reaction, generally product minus reactant. So if the product minus reactant, you get negative value. To find out the enthalpy of reaction, generally we take EP minus ER, energy of product minus energy of reactant. But in terms of activation energy, product minus reactant, this gives you what? A negative value. And this diagram is energy of product is less than energy of reactant. So product minus this is negative value. This is an exothermic reaction. This diagram is energy level diagram of an exothermic reaction. Okay. So energy of product minus energy of reactant. But in terms of activation energy, enthalpy of reaction del HR can be find out by enthalpy of activation energy of reactant minus activation energy of product. So remember, when you find out the enthalpy of reaction for any reaction, generally what is the energy of product minus energy of reactant, that gives you the enthalpy of reaction. Okay, that gives you the enthalpy of reaction. But in terms of activation energy, this should be activation energy of reactant minus activation energy of product. And if in a reaction, enthalpy of reaction is greater than enthalpy of product, then activation energy of reactant is less than activation energy of product. So this is some idea about threshold energy and activation energy. Okay. Next come to another part, that is effect of temperature on reaction rate. Effect of temperature on reaction rate. Okay. So in first or second class we have discussed what is the effect of temperature. So generally with increase in temperature, the rate of a reaction increases by 2 to 3 times. So generally by increasing temperature, the rate of a reaction increases, because the molecules get more kinetic energy. As they get more kinetic energy, they collide more easily with each other. In this number of collisions per unit volume increases. As the number of collisions per unit volume increases or collision frequency increases, in this the rate of reaction increases. So the relationship between temperature and the rate constant is known as, is given by one equation. Already I have told you, that is for every 10 degree Celsius rise in temperature, the rate of reaction increases to 2 times or 3 times, increases, it becomes double or triple. So that can be find out by the temperature coefficient, that is equal to, by the formula K equal to, so K T plus 10 by KT, KT plus 10 by KT, or generally K 35 by K 25 degrees Celsius. This value is nearly 2 to 3. So the rate of reaction generally increases to double or triple with rise in temperature. So with rise in temperature, this rate constant also increases in this way, this value. So this value is nearly 2 to 3. What is the exact relationship between this temperature and this rate constant? So this relationship between temperature and rate constant is given by Arrhenius. Okay, effect of temperature on reaction rate. So the rate of reaction generally increases with increase in temperature. Then effect of relationship between temperature and rate constant. So this relationship is given by Arrhenius. According to this, the rate constant of a particular reaction equal to A into e to the power minus Ea by RT. So K equal to A e to the power minus Ea by RT, where K equal to rate constant of a reaction. A is known as frequency factor, that is the collision frequency, you know, and this is also constant for a particular reaction. This is frequency factor. Ea is activation energy. R, universal gas constant. Universal gas constant. T, absolute temperature. And this small e is the exponential term. Okay, so K rate constant, frequency factor, exponential term, activation energy, universal gas constant, and T is the absolute temperature. Okay, suppose this is equation 1. This is the relationship between rate constant and temperature. Okay, to find out more accurately, then we have to convert this in, we have to express this in logarithm form. Okay, so taking logarithm both sides. Now, so you know what are the terms? Now taking logarithm both sides, what we get? Taking logarithm both sides, that is ln k equal to ln a minus Ea by RT. Ln k equal to ln a minus Ea by RT. So this equation is also called Arrhenius equation. Suppose if we draw a graph between here, so ln k equal to ln a minus Ea by RT. So ln k versus temperature. This is the relation temperature and rate constant. Suppose here in this way we have taken the temperature and here the rate constant k, ln k. Ln k versus temperature. Then it gives a slope. It gives this type of line. What is the slope? Slope of the line minus Ea by R. Slope equal to minus Ea by R and the intercept is ln A. So this is logarithm to the base e. If we express this equation to logarithm to the base 10, then what happens to this equation? So 2.303 log k equal to 2.303 log A minus EA by RT, or log K divide all by 2.303, we get log K equal to log A minus EA by 2.303 RT. So when log K versus temperature graph is drawn, then slope becomes minus EA by R with intercept log A. Similarly, when the graph is drawn between log K versus temperature, it also gives a straight line, but here the slope is minus EA by 2.303 R, and the intercept is here log A. Here the intercept is log A. This is only the difference, that is logarithm to the base E and logarithm to the base 10. Okay, so in this way, from this graph you can find out what is the activation energy. We can find out, okay, what is the activation energy you can find out, and what is the relationship. So K versus T, it gives this type of relationships. Okay. Next come to what is the value of rate constant at two different temperature. If there are two different temperature, then what happens to this relationship? Okay. So this equation log K equal to log A, by give it equation number 3. Next, temperature dependence of rate of reaction. Temperature dependence at a rate constant at two different temperatures. Okay. So from this equation 3, we can write out. Suppose the rate constant of a particular first order reaction. Suppose the rate constant of a reaction is K1 at temperature T1 and K2 at temperature T2. Suppose the rate constant is K1 at temperature T1 and K2 at temperature T2. Now substituting these values in equation 3, what will happen? So what we get? Log K1 equal to log A minus, for a particular reaction this frequency factor is constant and this activation energy is also constant, that is equal to EA by 2.303 RT. Log K1 equal to log A minus EA by 2.303 RT1, and so this is equation suppose 4, and log K2 equal to log A minus EA by 2.303 RT2. So where T2 greater than T1. Okay. Now subtracting equation 4 from 5, what we get? Log K2 minus log K1 equal to log A minus EA by 2.303 RT2 minus log A plus EA by 2.303 RT1. Log A cancels. So this implies that log K2 by K1 EA by 2.303 RT2 plus EA by 2.303 RT1. Suppose you take the value EA by 2.303 R. This is the common factor. So EA by 2.303 R, then what we get? 1 by T1 minus 1 by T2. This term positive and this term negative. That's a A by 2.303 R taking common 1 by T1 minus 1 by T2. Or that is equal to EA by 2.303 R T2 minus T1 by T1 into T2. This is log K2 by K1. So this relationship, this is the temperature, this is the equation for temperature dependence of rate constant, and this is the equation for rate constant at two different temperatures relating to activation energy. Okay, so for today up to this, and now let us discuss some numerical problems based on this. Now let us solve some problem. Okay, the rate of a particular reaction doubles when the temperature changes from 27 degrees Celsius to 37 degrees Celsius. Calculate the energy of activation of such a reaction. So the rate of reaction increase in doubles means the rate constant also doubles. So in this way, with increase in temperature, the rate constant also increases. Suppose so log temperature changes means log K2 by K1. What we have get? What is the formula? Log K2 by K1 equal to EA by 2.303 R T2 minus T1 by T1 into T2. Okay, so this doubles, that means K2 by K1 equal to 2 or log 2 equal to EA by 2.303 and R. So R is universal gas constant. This is universal gas constant, and this term is energy term. In this way, you have to put actually the value of R 8.314 joule Kelvin inverse mole inverse. So R value 8.314 joule Kelvin inverse mole inverse. Okay, that is equal to 8.314. So joule Kelvin inverse mole inverse, keep it in mind, into T2 minus T1. This is the absolute temperature. This is your T1 and this is your T2. Just add 273. You get this T2 and T1. So T2 equal to 37 plus 273 and T1. This is equal to 27 plus 273, that is equal to 300, and that is equal to 3110 Kelvin, absolute temperature. So into T2 minus T1, the difference is 10 already, whether in Kelvin or in, so 310 minus 300 divided by 310 into 300. Okay. So R value 8.314 joule Kelvin inverse mole inverse. And what is the value of log 2? You know, this is equal to 0.301. So what is EA? Then EA equal to log 2, that is equal to 0.301. So EA equal to all terms comes here. 0.301 into 2.303 into 8.314. So joule Kelvin inverse mole inverse. This is the unit, and again 310 into 300 divided by, so EA equal to all this term divided by 10. So this much divided by 10. This is the temperature, and temperature Kelvin. This cancels. This is Kelvin inverse is given, and this is the Kelvin square, and this term cancels. So what is the value of this value? So this value you can find. So multiply all this, just divided by 10. You get 53598.6. 53598.6 joule mole inverse, that is 53.5 53.6 53.59, so 53.6 kilojoule mole inverse. So the activation energy is 53.6 kilojoule mole inverse. In this way, so different term K2, K1, EA, R, T2, T1 is given. So 1, 2, 3, 4, 5. Among the 5 factor, any 4 terms will be given. Among the 5 terms, any 4 terms will be given, and you have to find out the another term. And R is the universal gas constant. For that, generally you put 8.314 joule Kelvin inverse mole inverse. This is the energy term. Okay, so either you may ask for K2 or find out K1 or find out K2. If the temperature may be given, find out the T2, or we may find out T1 or E1. So among the 5 variable factor, any 4 factor will be given and another factor will be asked to you. So here the activation energy is asked, and this value is 53.6 kilojoule mole inverse. For that, this is the formula. Okay. Next, come to question number 2. So here one reaction, but here given two reactions. Two reactions of same order have equal pre-exponential factors. That is the A is same, but their activation energies differ by 24.9 kilojoule mole inverse. Calculate the ratio between the rate constants of these reactions at 27 degrees Celsius. So what is the generally Arrhenius equation? K equal to A e to the power minus EA by RT. But here the temperature constant, two different reactions, A is same, and in this K are different. So what is the value of K1? That is equal to A e to the power minus EA1 by RT, and K2 equal to, at the A is same, A e to the power minus EA2 by RT. A e to minus EA by RT, this much. So dividing K1 by K2, dividing, or K2 by K1, dividing K2 by K1, what we get? K2 by K1 equal to A e to the power minus EA2 by RT divided by A e to the power minus EA by RT, EA1 by RT. So A cancels, or EA by this one. So e to the power minus EA2 by RT and e to the power A1 by RT. So what we get? K2 by K1 e to the power, so this term if comes here, minus, this is equal to EA2 minus EA1 by RT. So e to the power minus EA2 is minus EA1. So in this way EA2 minus EA1 by RT. This value comes. So what is the value then? Now substituting the value of T and taking K2 by K1 e to the power 24.9 kilojoule is given. So is R value put in joule. In this way I am going to put here the value of 24.9 into 1000 divided by R value 8.314 joule Kelvin inverse mole inverse into T 27 degrees Celsius, that is equal to 300 Kelvin. Okay. Now taking logarithm both sides. So this value, if you divide 24.9 1000 by 8.314 and 300, you solve this and you find that is equal to e to the power 9.983. Now taking logarithm both sides, ln K2 by K1 equal to 9.983 or log K2 by K1 9.983 divided by 2.303. Now ln equal to 2.303 log. So 2.303 value is divided here. So that value equal to 4.3348. Okay, log K2 by K1 equal to 4.3348 or what we get now K2 by K1 equal to anti-log of 4.3348. So K2 by K1 equal to anti-log of this much logarithm, then take anti-log of this much, and this value equal to 2.162 into 10 to the power 4. 2.162 into 10 to the power 4. So this is the ratio of rate constants of two reactions. This is the ratio of rate constants of two reactions which have same pre-exponential factor and same order of reaction at 27 degrees Celsius. So these are some examples and you will solve this type of problem, and later we will discuss some other questions.